Now consider some applications of this modular differential operator. Or let me call them examples. First of all, I would like to consider the case of Jacobi form in one variable. So, first of all, we consider Eichler-Zagiers Jacobi forms. The Jacobi form of Eichler-Zagier of weight k and index m are, in our notation, Jacobi form of weight k for one-dimensional lattice 2m. The lattice generated by a vector with square 2m. If we write down the Laplacian of any positive definite lattice, this is the square of the covector E I star D Z E from 1 to n0, it's scalar square, but EI star a basis of the dual lattice. So we have here s to the power minus 1 d z, where s, this is the gram matrix of the lattice, L, and d over dz we write as a column vector. In our particular case, in the case of Eichler-Zagier, the lattice is 2m, and we get here 1 over 2m d square over dz to the square. This is the Laplacian part of our operator. So the operator h k, in our case, let's analyze its definition once more in the general case. For the operator h, we use the following normalization: 1 over 2 pi I and then 1 over 8p to the square. So now we have 1 over 2 pi I delta tau plus 1 over 8p to the square and 2m gives us 1 over 16p to the square m. This is the operator hk, which transforms Jacobi form of weight k and index m into the space of Jacobi form of weight k plus 2 and index m. Now I would like to make some concrete calculation. Let's consider the space of Jacobi form, weak form, of weight minus 2 and index 1. This space is generated by Jacobi form of weight minus 2 and index 1. And for this function, we found the explicit formula in terms of the Jacobi theta series. This is the square of the Jacobi theta series over 6 powers of the Dedekind eta function. And this function starts by the following Fourier expansion: r minus 2 plus r to the power minus 1 plus q multiplied by something, where r, this is e to the power 2 pi I z. So let us calculate h minus 2 at phi minus 2, 1. Then this is equal to 1 over 2 pi I d tau plus 1 over 16 p to the square d square dz to the square phi minus 1 plus the weight is 2k minus n0 g2 times f minus 2, 1. But k is equal to minus 2 and n0 equal to 1. So here we have to put minus 5 in our case. So n0 is equal to 1. Now I would like to calculate the first. It's better to say the zeros term, the zeros Fourier coefficient in terms of the variable q of this function, because according to our theorem, this is a modular form of weight 0, a Jacobi modular form of weight 0. The first term will be related to this operator. So we get 2 pi I to the square over 16 p to the square e to the power 2 pi I z, and the similar factor for minus z. Then the next terms will come from this multiplication, from the operator of multiplication by G2. By G2, the quasi-modular Eisenstein series starts with constant term minus 1 over 24. So means that here we have plus 5 over 24 times e to the power 2 pi I z, then plus minus 2 times 5 over 24, plus the similar symmetric terms for powers of that. So I simply add plus for minus z. We get so here we can simplify pi, we can simplify 2 by 4, and we get here minus. So 1 minus 1 over 4, it gives us 6 over 24, so we have minus 1 over 24 r minus 10 over 24, and by symmetry 1 minus 1 over 24 r to the power minus 1 plus q something. What we get? We get then minus 24 times h minus 2 phi minus 2, 1 is equal to phi 0, 1 tau z. This is a function, starts with the following Fourier expansion r plus 10 plus r to the power minus 1 plus q something. And this is a weak Jacobi form of weight 0 and index 1. This is the function which we constructed using as a modular differential operator h minus 2.